Okay.
Thank you.
So thank you to all of you for being here. Michaela entered the room and this was noticed. She cannot enter without making it clear. And so thank you for being here. Today is, as you know, a great pleasure to have Bogdan Suceavă. What is the right pronunciation? Suceavă. Bogdan Suceavă talk on the comparing Nicole Oresme concept of Curvitas with Bernhard Riemann's definition of curvature. The usual practice here is that if there are clarification requests, they can be done during the talk if you do not disagree. And then there is a final discussion on more substantial issue. So what should I do now is to share the screen. This is done. And then to go, this is come likely, and then to go full mode screen, and then this will make this to work. So Bogdan, that's to you.
Thank you very much. Thank you very much for the invitation. It's been too long since I didn't deliver a talk here among my friends at Chapman. It's a great pleasure to be back again. That's about it, about that break. And please go ahead and, it's for any kind of questions, most welcome at any time. There's absolutely no way I can forget what I mean to say. This is it's a very interesting theme. And the challenge is actually due to a paper that Julian Coolidge wrote right before his passing. It appeared in the Monthly. And he wrote that the story of curvature is unsatisfactory. Okay, let's see what it means by this. He writes, the first writer to give a hint of the definition of curvature was the 14th century writer Nicole Oresme, whose work was called to my attention by Carl Boyer. And here's the truth. There was no translation in English at that time, in the 50s. And it wasn't really clear where in the work of Oresme was actually needed. I mean, why in the world a monk in the 14th century needs curvature? That is a question, and we're going to have to explain that. That's a little bit of a challenge itself. And we're going to have to, understand the whole doctrine before we're getting into it. And I bet you already know quite a little bit of that. You will see why. Then Coolidge comments, Oresme conceived the curvature of a circle as inversely proportional to the radius. How did he find this out? And due to Marshall Claggett's investigation, we can actually pinpoint what the sources were, and that's it's kind of clear. So the fact is this: the definition appears at the middle of the 14th century, and this is kind of funny because there are not too many things we can, mathematical concepts that could be traced back to the medieval Western Europe. So having such a fundamental concept invented at that time, how is this? And then what was the impact of the discovery? Did anybody use it? Okay. So Oresme's reasons are not related to the mathematical motivations the later authors pursued. He had completely different reasons. We are on a different planet with reading him. Now, here's the thesis that we are going to argue about today. Oresme introduced the idea of investigating shape. We're going to have to look at the doctrine of configurations. At the same time, we're introducing the idea of deformation of shape. Now, if you're looking carefully at this, we do have something similar in Gauss's Disquisitiones in 1827, but that's about surfaces. It's a stroke of genius about surfaces. But then the same idea appears in Riemann. That is, we're investigating space and the deformation of space. What is truly bizarre is that with Oresme, we don't have, of course, the quantifications. There is no way he's indicating how to calculate it. he's discussing it. And we're going to get into a very special literary genre. That is, he's going to make claims that are 100% true. But the way he's proving and arguing is completely different than what would you expect. That's what's going to happen next. So everything has to do with the recovery of Aristotle. That was the fact that copying or retranslating most of Aristotle books, coming back from some of them from Greek sources, most of them from Arabic into Latin. And then there was another problem because at least Charles Lesage didn't like to read in Latin, and he requested translations into French. What did he request? We'll discuss in a few minutes. But anyways, in that interval of time, 42 books from Aristotle have been translated. And some of them were intermediate translations. One can write a thesis about how much the original content has been deformed and misunderstanding happened. It's actually a serious topic. And that's actually a third of the whole content of Aristotle's work. Quite a bit is lost. We have works whose existence is mentioned by other medieval authors, but they never made it to us. It's a fact. Now, most of these translations have been done in Spain, and a lot of work was actually intermediated through Arabic sources. And it's a whole story about, we could take each piece of each book and pretty much trace it back to see how it made it to Western Europe. Basically, we're going to be interested in the categories because it's the categories that actually had that little detail that triggers Oreme's interest. Okay, so categories was actually translated in the 6th century into Latin, so that was available for a long time. Actually, St. Augustine describes in the Confessions how he was overwhelmed by reading the categories when he was 20. Boëtius had a more ambitious project to translate into Latin and comment upon the whole work of Aristotle. He didn't have that much time. Now, there is something hidden in Aristotle text. The idea of continuous measure. Of course, using the word measure means a lot in analysis, in probabilities. It's a very important concept. I think we can discuss for a few days what measure means in Aristotle's work. But the idea of continuity, that's important. So let's take a look at chapter 6. And by the way, this is actually following Marshall Caggett's remark. So let's go on text and see exactly what's going on. So discrete quantities and continuous quantities. Now, continuous quantities, as a particular category in there, we have space, and another one is time. Well, that's all he needed. Orem. Because the two categories we have here is, in this translation is place, that's for space, and time for sure. And that appears several times in the text. A line, on the contrary, is continuous, or you may take a common term, which is parts, namely a point. And then he's discussing about surfaces. And the idea, you have the concept and the continuity is right there. Now, if you're looking very carefully, this idea of continuity is really becoming precise in the 19th century. But there are so many ways in which it was used before. Okay, so think like this.
By the way, what the topic of the last talk?
I noticed that was so nice. It was a pleasure to follow. It was like, okay, nice. I like that. Just imagine the following: that you have the Bible, okay, which you know by heart. You have Isidore's etymologies, with which you might disagree. And then some Euclid, we know precisely where he read the Euclid. It was in the context of Collège de Navarre. And by the way, this is not Université de Paris. This is different. The quality of mathematics wasn't the same. But no Apollonius of Perga, none of the advanced treatises of the old world made it to him. Not yet. No advanced geometry. And based on this, go ahead and come up with a doctrine in which, among the particular things, he's discussing the formation of space. I mean, you look at the evidence and you wish that guy to have been a math major in a modern university, but we're dealing with the 14th century realities here. So he derived valid mathematical assertions with very limited technical background. That is the truth. Back to Aristotle. Place, that is space, pertains to the category of continuous things. That's something that he read in Aristotle, and Marshall Claggett points out that he relies on Aristotle. He's deriving everything he did. He's referring to the Magister. Okay, so that was the detail. That was, yes, please.
It seems like your screen sharing is false. Can you check the video?
What the problem?
It says your screen sharing is false.
Yeah, maybe we just started and stop.
Yeah, or not, or just pick the yellow, pick the yellow.
Would you come here and do it? Because I'm not sure what I do and I don't want to interrupt the. Yeah. Thank you. What have I done?
I don't know. Just not shown it, disregarded the people on Zoom. There, resume share. For some reason, it just doesn't want to do it.
Exit and enter again.
Yeah.
That's really just stop it.
Stop share, share again. Yeah.
Stop share.
I clicked on it. Okay, let's try share again. Bogdan, which is this one it is, right?
Hope so.
Acrobat?
That one, yeah.
That's the only one that should be. But maybe back and forth. It's good. Yeah,
Yep.
now it's green. Sorry.
Thank you, Michael.
Oh, no, what is it?
Save my day. Thank you. All right. So back to continuous measures. Now the moment we're gonna zoom in on is the decade starting with 1350s, because this is when the work was written, and there was a lot of disruption at that time. And we're gonna take a look at the whole context at Collège de Navarre, because you see, there were not really when you're losing a lot of faculty and student body, you can't really have any sort of continuity. And it was a miracle that the documents made it. And he wrote quite a lot during the Black Death. We're gonna look at that decade. What he's writing about, and he has quite an extensive part of his work. He's doing this. He's looking at the intensity of perceptions. He's talking about the intensity of pleasure, the intensity of pain, the intensity of joy. These are like subjective facts. Nowadays, I mean, when you're going to the doctor's office and the doctor is asking you how much does it hurt on a scale between 0 and 10, that's a subjective perception. On the other hand, if you read Orseme, these kind of subjective perceptions are given as certain quantities that could be measured. He's talking about that. He's giving these as examples. He has, I mean, in terms of applied mathematics, I don't know. Some of the themes are kind of uncertain. But while the other things, they do admit contemporary models in terms of applied mathematics. We can discuss about that, how much applied mathematics is in Orseme's examples. That's another interesting question. But in any case, this used to be the skyline, how it was about that time. It's the first decade after the completion of Notre Dame. So, for what purpose? Applications to architecture or constructions? No. In the treatise on the configurations of qualities and motions. So how do we know that was written between 1351 and 1355? This is due to a doctoral dissertation by Claudia Krenn back in 1965 at University of Wisconsin. And we can actually track it year by year what Orseme did. That's actually something that's her work. And paragraph that made it to Julian Coolidge was this. Consider two circles with radii AB and AC. If the radius AB is twice the radius AC, then the curvature of the smaller circle is double the curvature of the larger circle. All right, so pretty much curvature is 1 over R. That's 100% clear. Now, it would be interesting, and it's not entirely clear whether there is any other previous definition to this. Apparently, this is the first. This is the first that made it to us. And that's the historical context where it's coming from. What's really interesting is that he's developing it and he's using it. Okay, so let's take a look at the intuition. Like, how do we define it today? How do we define it in calculus? What's going on there? So suppose you have a curve parameterized by arc length, take the unit tangent, and measure the rate of change between the unit tangent vector and the arc length, and take the magnitude out of it. Okay, I just said here things that are definitely pertaining to the 17th century, because the idea of rate of change appears after what? After 1690, really. Then what? Then you can define acceleration, take the curve parameterized by the arc length, and the magnitude of acceleration is actually the curvature. It's one of our, you can define it this way. Well, he's using the word acceleration, but it's not the second derivative. He doesn't have these concepts. So what's going to follow next, I'm going to show you statements that are absolutely amazing, totally true, but without the concept of rate of change. How far did he go? So in conclusion, he's accurate, and I don't want to sound sarcastic, but in a 14th century kind of way. Because the assertions are true, but we have to make an effort to actually read that. And again, it's like reading Aristotle plus another little bit, because he's actually talking about infinity. He's adding quality to this. Talking about infinity, that's a difference between the Greek world and Orseme. Okay, so the problem was, how did he find this out? Well, we incline towards the following. By reading Aristotle and being part of the intellectual environment at the Collège de Navarre. If there were any other assertions circulated at that time, we don't have any proof about it. On the other hand, he needed curvature in the doctrine of configurations. Here's why, and this is actually something that you would never expect to need curvature. Take, for example, an assertion. So a proposition. And Oresme is interested in the following, right in the first part of the configurationibus. How people deform propositions. Like, perhaps I totally believe something that I witness. But then when I'm going to tell this story, the assertion becomes deformed. And there should be a way of measuring how the truth is deformed. This is really strange. So this is part of the motivation. Okay, so he had one serious problem against astrologers. He believes, there are people of good faith that sometimes are making false claims. Why does this happen? Okay, so the polemic against astrologers is pretty well known. He basically classifies, he gives 9 categories of astrology, and he's telling, some of them are perfectly legit, like observing how the stars move and so on, that's legit, while the claim of being able to predict the future, the art of divination and so on, that can be true. And he has a very serious philosophical and theological argument why it shouldn't be believed. Now, how much was he believed at that time? It's complicated also. We'll discuss in a second. But anyways, how about applying curvature to them as a measure of truth? Okay, that's unexpected. So he was born around 1320. Some authors are citing 1323. I don't think we have documents. That's today Fleury-sur-Orne. If you're going to Cannes, if you blink, you miss it. It's a small neighborhood nowadays. And that's the only portrait we have. Okay. He's coming to Paris sometime prior to 1342. His major was theology in the end. He was a bursar at the Collège de Navarre and then becomes a master. Now, this is non-trivial. It's actually to find how Collège de Navarre actually looked like. And anybody remembers the story of François Villon? Because François Villon actually, in the Christmas day, committed robbery in that cathedral, but that's in a different historical period. And François Villon has stolen 500 pieces of gold, which was discovered 6 months after it's a complicated story. Anyways, that's the location. Now, what do we have there? We have the dormitories. We have a library. I don't know where it was. We cannot visit it, of course. We have a church in there and that yard, okay? So the buildings must have been looking like this because are the only ones left standing with this architecture. Think about the following context. You have dorms and you have many students hosted in these buildings when the Black Death hit. We know that in 1348, Oresme major was in theology. We have no idea when he got the master's degree, but in 1356, he's a doctor. And he learned a lot by heart, including Aristotle, which at that time was okay to read at Université de Paris as well, because there have been some problems in the case before. Anyways, Jean Buridan and Albert of Saxony were among his masters, and he's writing while at College de Navarre this very interesting work, the Proportionibus Proportionum, which is algebra before the formalism of François Villon. That's of Viet. That's actually Viet's formalism appears later on, about the time of essays of Montaigne. It's later. So he's doing algebra before, and he's working with algebraic quantity and leading to sequences and series. It's something that he was interested in. Then about certain things, that's another work he wrote at that time. It's interesting today for the history of ideas in celestial mechanics. Well, let's take a look at the works. So that's before 1350. We know for sure that he read Euclid. While reading Euclid, he was reading also Aristotle. Then he's going to translate this in vernacular French, the book on sphere. And then Aristotle's physics is commented. Then the configurationibus is already a mature author at this point, while also doing algebra. Took a whole decade to finish these two books, and it was not really clear before Claudia Krenz made it very clear about that. About 1355, the configurationibus was completed. And then very interesting, in 1358, De Moneta, which is the work that was actually cited by Copernicus. As you know, that Copernicus was interested in currency and so on. So Copernicus knew of this part of Oresme's work. That's well documented. Now, I don't think we know the full story, but nevertheless, he has to quit College de Navarre after 1361. But then the luck changes 1 year later when he's becoming a canon of the Rouen Cathedral. And then did he have the king's support and understanding? Perhaps. That's conjecture. And then he writes more. All the polemic against astrologers, it's on. Because it was this problem about how much astrologers actually do have political power and political influence and ability to advise the king. And the Livre du Ciel et du Monde, it's also about the time when he's becoming bishop. So he's going to become Bishop at Lisieux, 1377. He died, I believe, I don't think he was 60 yet, 57, 60, depending on where he was born. Well, that's about the life story. And the king, which was a king who liked to read, who was very much interested in Aristotle. He was very much interested to see Aristotle in French. And definitely there was a battle there about who has the king's ear. And in the same time, this is important for us because we like to understand for whom was Oresme writing. You don't have too many people in the potential audience for this. Was this the king? Was this the scholarly environment at College de Navarre? Was this maybe potential sponsors outside the context. Yes, please.
Sorry, the Collège de Navarre is what become then the Collège de France, right?
I don't know if this is true. It was founded in 1305, and the buildings have been destroyed in 1811. I'm not entirely sure about the history. You might know better.
But I can be wrong. That the Collège de Navarre was transformed in the Collège de France in the beginning of 17th century.
Mhm.
In the first part of 17th century. True. I have not my computer.
No, it
computer.
was by Napoleon assigned to École Polytechnique in 1805.
No, this is later. The Collège de France was there. Robert Valle was a member of the Collège de France. So well in the 18th century, 17th century, and the Collège de France is still existing today.
So Wikipedia says it was one of the historic colleges of the University of Maryland.
And it is not saying nothing there. Whether when it finished.
Rather than this was born in the United States, it doesn't exist in this curriculum part, and then it is transformed in the École Polytechnique.
It was transformed in the corporate technique, so it's not the same. Okay, okay, so it's not the same that the Collège de France. So there are two different things. Okay, thank you.
I had no idea.
No, no,
That's
okay.
right.
You know
But here the
why it
format
was
is there.
called Navarre? Yeah.
Sorry?
Why was it called the Collège Navarre?
Navarre,
Jean.
yes.
Because the King of France was the King of
The
France.
queen made the first donation in 1305. It had to do with the queen's heritage and culture.
In a certain period, the Riemann of France was also Navarre.
Mhm.
And still today, when you wanted to say in France to everyone, you say, tout le monde de France et Navarre. It's something that is still. So it was part of. At that time, the kingdom of Navarre was independent.
Yes,
Yeah.
yes, exactly.
But
Yes.
what,
Mhm.
at that time,
That's a-
yeah, it only became part of the domain with Henry IV. In what? With Henry IV,
Now we will have-
1590 something.
Okay.
Okay.
Sorry, I did my homework only for the 14th century. So it's some of the works, including all that, very energetic rejection of astrology, was actually written with the hope that maybe as much the influence they had over the court was limited. Now, who was he writing for? Because he, if you're thinking about the arguments you're going to see, he's really trying to convince people. He's trying to persuading people. And I owe to Edward Grant a particular remark that, at least in Oreme's works, every time when he's citing the Bible, this is not like an argument coming from the Bible. He's just trying to relate with audiences, and there is some scientific truth that's right there, and you're using every argument at your disposal for expository matters, including the religious text and whatever is the common knowledge with the audience, the target audience. And that's how you read Oreme. So he cannot pull up Aristotle. He's pulling up the images and the references that are the most common at his time, which makes, I have to admit, took me a while to understand how to read Oreme, right? I remember when I started to read, I read the first book and I couldn't understand the word. And then when it clicked, suddenly I said, stop, go back and start reading again, because it has to be read like you read Aristotle. It's really like that. Okay, then after 1370, there's something going on here, because he's becoming one of the king's chaplains. And this is how he's invited to translate 3 of Aristotle's books. Now, if you're looking in terms of the translation work, this is something that today you wouldn't pass any sort of editorial process, because he's not confident in Greek. He's translating from Latin into vernacular French, the French at that time. All right, so we don't have some of the books. We know that they made it from Arabic into Latin. So this is like a fourth translation. There is a serious deformation of content in there, and this was studied. Okay, this is, but again, this has nothing to do with the main theme we discussed today. Now, if Gaimard says that these are, two different languages, and if nowadays we have two different texts, one in the medieval French and one in contemporary French, we can see that his translations pretty much are works of the 14th century. That's a language that has its nuances, its own different style, and it's quite interesting. And by the way, it is possible that Nicole Oresme was rather political adversary with Thomas de Pizan, Christine's father. That Tommaso being one of the astrologers at the court. So back to the matter at hand. So we have 93 books, and the first 40 is setting up the doctrine of configurations. He applies the doctrine to qualities, focusing on entities which are permanent or enduring in time. All right. What is he talking about? What are these configurations? You know what? This is an early theory of functions. Okay, this is what's going on. But for Oresme, there is nothing like the vertical line test. So we have relations, but the particular case of functions is not really well defined. He's discussing starting from representations. So this is what he's building. We're like what, 320 years before Newton. And he has to make it from scratch. Go ahead and build up the theory of functions based on Aristotle and the idea that certain things are continuous. This is what's going on. And then as applications, well, he's trying to describe some physical processes like, the movement. That's right what you should do if you're discussing about functions. Of course, movement is something right there. But then a lot of the examples he's using are psychological phenomena, something that you don't find today in the calculus books, right? This is not something you rely on because we don't have accurate quantifications. But he's not doing any sort of quantifications. You don't find numbers there. He's just discussing, well, theoretically, how would that be? And he's using it as example. That's book one. In the second part, he's describing pretty much those graphs-like structures, and they are to be applied to entities that are successive, in particular to motion. And then he's discussing, I'm going to mention a couple of really surprising classes of examples he's using, including magic. It appears a couple of times. Why not? What really interesting is what's going on the third part, which has only 13 chapters. He is talking about surfaces at some point. So he's going multivariate here. He's going in 3D. Why not? Describing qualities and motions. And then at some point, he's doing something that's very Gauss-like. He's comparing areas. Saying, the areas could be compared. This is incredible for the 14th century, and we'll go on text. So every measurable thing except numbers is imagined in the manner of continuous quantity. This is clearly straight from Aristotle. Then he spends a lot to argue that certain qualities can be figured. Like, okay, it's okay to draw graphs. Because for the first time when it was ever used, graphing configurations, that happened like about 10 years before. It was another author in Italy, of which very likely Oresme wasn't aware. So he has to invent all this. He has to come up with this stuff by himself. He's indicating the Magister as the source. Now, part 1, chapter 11, Oresme talks about uniform versus deformed qualities. And he's talking about simple deformed deformity. What's that? Well, all these names, what do they mean? Well, today we have all sorts of things. Like, for example, a rectilinear graph, a curve in general position. Everything is today very precise. At that time, there was nothing like this, and he's coming with some monsters of expressions which pretty much means a curve of different kinds. In 115, he says that there are 4 kinds of simple deformity, and he's explaining that by drawing. He's classifying graphs based on convexity and concavity. Okay, now there is nothing about second derivative, nothing like this, of course. Then he's mentioning surface quality. It appears, I believe, in 119 first. Then he's going to pick this up in the third part. And then in 119 to 121, curvature appears. So if you're thinking about curvature in modern terms, what's that? It's kappa of S. That is, makes very precisely the location where you measure it. And kappa is actually the actual measure of curvature. He's saying this. It's endowed with both extension and intensity. Extension means the location and intensity. He got this right. Okay. That's in 120. In Claggett's translation, we do not know with what or with regard to what the intensity of curvature is measured. Of course, he doesn't have the arc length. And he's honest enough to say it. That we don't know, it's quite amazing. For now, it appears to me that there are only 2 possible ways to talk about it. The first is that the increase in curvature is a function of its departure from straightness. Amazing intuition. That is, of its distance from straightness. This is to be measured by the quantity of the angle constituted of a straight line in a curve. That is, the angle of contingence, or perhaps another angle also constructed from the straight line in the curve. Now, what's amazing here is if you want to prove that, you have the d phi over ds, its curvature, that you need to pull up, the Frey formula in the plane and prove that. That's an amazing piece of intuition. This is the kind of
all the angle z is an infinitesimal angle.
For
and this is already discussed by you. So that's is a non-Archimedean quantity.
okay.
If you take the angle between the circle and the tangent to the circle, of course, then you can take the line as you want. But generally, the whole angle is the angle between the circle and the tangent between the circle and the tangent, so that they can be talking around this.
I happen to remember exactly the proposition. Where is that? It's book 3, proposition 32 in Euclid. 332.
And that is Euclid that shows that it can be made smaller than Euclid, so there is not Archimedean.
But for curves. For curves.
Yes, for circles.
For circles.
Yeah.
We're talking here about curves.
But it should be the same thing, because it is the tangent.
Oh, it's a whole world of a difference. When you're moving over from a circle to a curve in general position, maybe I'm abusing the language here. But when he's talking a simple deformity that admits,
Can you draw? What does it mean?
definitely. So when you're looking at Euclid, what you meant
Exactly.
is this. This is what you meant.
And no. What I meant is this one, is the angle between the curves and the circle. That is this angle here. And this is the Orsme angle, and it's not the angle, it is a curvilinear angle, with the circle and the tangent here. This is what we can call the Orsme angle. And Euclid, and don't remember where, that this is not Archimedean magnitude. So it can be made smaller than any other quantity.
Then more
The
investigations.
problem is that if you go to take these angles here, and the problem is how you calculate this part here. So why it is not this or this, why it is. So the angle should be this one. It is not a rectilinear angle, but a curvilinear angle. The problem is that this is not an Archimedean angle. At least for the circle, but I don't think why it should be different for any curve. if this is the tangent.
This is extremely important, and I think we're left from here with one question. If there is any way that this would imply that in 119, that I don't know, because chronologically it's possible because he read Euclid, we know that.
Okay.
I will have to think more about it. So here I'm gonna say I don't know whether there is affiliation of ideas here. That would be really interesting. Okay, but that's, you will see why is this important, because can I move on the topic? Now the rate of change for the turning angle with respect to arc length is curvature. This is what I mentioned before, but that's really 19th century. That's really later. And there is something else that I should point out here.
The configuration angle that you were talking about, you have a certain proportionality when you have a circle, when you have a general curve, you do not. So, I mean, that's basically the difference. You have to quote unquote, you have proportionality, you move away. You move proportionally, we're in a circle, but on a curve, you do not. So just, I mean, that's one thing, one difference, for example, in general curves.
That's one way to look at it.
Yeah.
Anyway, this is not legit because I'm starting with axes. This is not 14th century what I'm doing here. So I apologize big time. So
Well, it's magic in 14th.
No, but I understand, but the point is whether, of course, if you take that argon delta,
Sure.
that you are right. But what is said to me, the quantity of the angle constituted by straight line and the curves, if I understand well, what is the meaning of this angle here? I'm saying wrong, but this is the angle constituted by the straight line and the circle.
You take it when?
That's the point. That's exactly the point.
With the circle proportion, proportional, with other curves, it's not, it depends on the point.
But it-
Whereas
Is a-
proportionality is independent. on the curve. Anyway, so, yeah. Well, I'm sorry.
So anyways, no, what I argue here, I think we should give Orseme points for the grade for raising the problem. Like that's all I'm saying. Because there is no quantification here and any debate here when we don't have really there is no formula whatsoever. So he got that part for, for the circles. That's a quantification we do have. He's giving us that kappa is 1/r, that's clear. But beyond that, he's discussing about the matter without really measuring it. I mean, if your student is doing that in your calculus class, what grade would you give?
Yeah.
Don't do that here. This is 14th century. So that's what I'm saying. And we have to learn how to read it in a 14th century kind of way. Okay, you would expect kappa equals magnitude of ds over dt. We don't have that, but the idea is there. Okay, so let's take a look at how the text is written. So this is the Marshall-Claget's edition, appeared in 1968, which again, it's important for the chronology because Julian Coolidge didn't see this. This appeared later. We have all these graphs in the text. We can clearly see what he meant. He's illustrating it. There's a discussion on cases. These are really graphs of things that look like functions. He's just not very precise about the definition. Okay. In some of the copies, later copies left from the 15th century and 16th century, there's like really tragic thing happening. The drawings are done on the margin. So that we're kind of losing the continuity of the text, unfortunately. But this must have been a very difficult editorial piece of work to reconstruct it, really. And here's one of those very strange examples on the deformity of joys. One ought to speak in the same way concerning a joy or a pleasure, which is supposed to be a certain quality extended in time and intended in degree. Okay, but how do we measure joy? Okay, for example, right now I'm very happy. I'm on a scale between 0 and 10, maybe a 9. No. So this is subjective.
That is a great compliment for us.
I'm trying. I'm trying. Oh, come on, Drew. No, give me some help here. No, I'm working only with integers. It's a discrete measure. All right. Okay, so here's an addition. This is from the library in Florence, and all that amazing discussion on convexity and concavity is right there. And if you're looking at the quality of the figures, there is some serious art. I mean, this is coming from somebody who touched Euclid. There's no way you can do that if you are just a theologian. And I don't mean to say anything bad about that. It's just there's some science going on here. So the copists who moved the figures on the margin knew how to draw circles. That's excellent. Okay. So let's go back in part 1, chapter 20. Every deformed curvature is, by the way, he's using the word curvitas indistinctly for curve and curvature. Sorry, that's how it goes. Every deformed curvature is deformed in a way different from that in which any other quality of another kind could be, and so it is deformed with a strange, marvelous, diverse kind of deformity. Stop for a second, erase the words that could be assigned as a metaphor, like strange, marvelous, diverse kind, and think of replacing them by unique. Like the curvature uniquely characterizes shape. I almost ready to buy this, except that here we notice the first important failure of this. And again, we shall not take points off. In modern theory, we have curvature and torsion. Curvature and torsion uniquely determine the shape. That's Ossian Bonnet, right? Was that 19th century? He does not distinguish between curvature and torsion. Of course, Anglais de la torsion, that's what, 1805, later. But nevertheless, the statement looks like the fundamental theorem of curves. So he's defining a configuration, because that's what it is. It's a quality. And that quality characterizes shape. So if you have kappa and tau, you determine the shape. That's the fundamental theorem. How do you prove it? You need a little bit of ODE there. So you need really 19th century. That's one of the most amazing pieces of assertions that you find in Oreme's work. Okay, so curvature and torsion are different invariants. Ferenczi equations proved after 1847. Oreme's doctrine doesn't distinguish between them. So Curvitas is actually amalgamating these two quantities. That's what it is. Good. Quite remarkably, he has counterexample of qualities that don't fit the doctrine. He's writing a quality of an indivisible subject, such as a soul or an angel, does not have extension.
But are you sure that possibly it's a stupid question that Oreme is speaking of curves on the space but not in the plane?
Some of them are in plane, some of them are going to be on surfaces. Most of them are actually in the plane. So in that sense, if you allow that tau is 0, then he's right on the dot with the fundamental theorem of curves in the plane. No problem. Except that he's not aware of this distinction. I mean, in one single word.
I understand that he's not aware of the distinction, but if you are always in the plane, the distinction
doesn't matter.
Making sense.
Doesn't matter.
So that is the question.
Definitely,
so
definitely so.
The point is become interesting if you are looking it on the curve gauche, come on, the curve gauche, the curve in the
in general position, twisted curve, that's the language. Twisted curve. Yeah, so no, he's talking about movement on surfaces in the third part that I remember. I don't remember precisely where, but most of the configuration he's talking about are graphs of curves like in Calc 1. Okay, then he's right. But again, if you're talking about an early theory of curves, and if you're dealing with this, you have to honestly mark what's missing. Missing vertical line test for functions, missing torsion. That's what it is.
But a vertical test for function, this is essentially what needs Cartesian coordinates, right?
Yeah, so, well, let's remove that. Let's work on Venn diagrams. So you're saying here's the domain, here's the range. So I want to associate to this element, one element from here, one and only one, really. So it's one arrow. We're not doing here complex analysis with multi-branch graph, nothing like that.
Yeah.
So what are required to cut?
No, what I mean is that you sometimes use the word curve and sometimes you use the word function. And a function is can be understood, the graph of function can be understood as a specific kind of curve. While there are other curves that when you represent them in a Cartesian plane, they don't satisfy the vertical line.
That is historically true, but we have to consider that the Cartesian coordinate was invented by Coulomb. So there are something similar. Of course, they are not exactly Cartesian coordinates, so they're not function, but they're simple. They're not equation, but they are proportion. But essentially, the basic idea behind the field is already here.
My question is simple. It is that if you have a circle, it's a curve, but it doesn't satisfy the vertical line test at all. So it is not a function.
Of course.
Right, as we understand a function.
Totally it is, on pieces it is, that's the problem, so
But,
it's trying to hold the dimension.
but, in a-
That's what it's here. So any curve, which is one dimensional manifold, locally, it's parameterized by a parameter T, can be embedded in our 1+2, which is our three. So anything that's one dimensional and smooth can be embedded in our three. We can see, so there's always going to be a continuous coordinate. So you can actually see these wise, it's going to be always.
Yeah, okay, but globally it doesn't satisfy it, but.
Yes, but if we are speaking,
Yeah, that's what
if we are speaking on curvature, we are speaking on the local curvature. Locally speaking, on a appropriate interval. Appropriate hyperlink of the point.
X equals X 15 satisfies it, Y equals Y satisfies it, so that's what it does.
But
Yeah.
I think the vertical line test. This requires an orientation of your curve with respect to some particular system, and then but the curve is independent from any of these, right? So
But if Alex in Wonderland, which way is up?
Okay, I apologize for, so this is my error. I have used this slang metaphor, vertical line test. What I should have said, and that was more accurate, it's a law of correspondence between domain and range.
okay,
There is no, I didn't see any sort of clarification of this. And I believe that's the problem. Why we say that? I mean, the polite way to say it is an early theory of functions where you don't really have clarified these matters that are actually becoming precise when you develop the theory, the modern theory of functions. And we can discuss when this appeared really, because we can either go to the 17th century's approach or we can go with axiomatic constructions from the end of the 19th century. So there's really something that's a vertical line test is a way of saying, and it's more associated with the algebra 1 classes in, in American middle school or high school, depending where you see it first. It's a way of saying it. So don't look at the way up or the way down. No, it's just a name of between a relationship between domain and range.
so you're saying that
Yeah.
there's no clear distinction of the function versus multifunction.
Yeah.
The univalent
Relations,
function of multiple
relations.
functions.
Yeah, so he's spending like what, 4 chapters to just to argue that, you know what, you can draw graphs. So he didn't.
There is no function. There is no notion of function.
He's speaking about functions since the beginning, so.
What I'm saying is that these configurations are earlier. It's our early theory of functions. This is the configuration.
Yes.
That's
we
what it is.
can, yes.
But at this time, historically, there's no function.
I see the plan.
No, it's an important discussion. We really have to look into this. So that there are so many things.
The basic idea is the basic idea that you learn in the study of what you call the intensive quantity, intensive quality. So,
Mhm.
and then not only the Orseme, but also in the Merton College, more or less at the same time. We did have to associate a certain magnitude, that there was not a measure that might express by the segment with a certain point or a certain time. Of course, there is no dimension function, but the idea that there is a variation of the quality in such a way that for a certain point, with a certain time, you can associate the magnitude that in some sense express the intensity of the quality. Okay,
And
for
while we do
example,
that,
this is not a red in the same way. In this point, the tension of red is expressed by this segment. The other point is that center. So now we talk a bit of the function.
so what I thought that, this is very important because what we discuss here, we're discussing about space and its deformation. I'm interested in this duality.
Yeah.
This is actually, it's like, I cannot discuss space abstractly. I have to discuss its deformation in the same way, and I have to say something about it. And he's making this construction. It's an intellectual construction he doesn't have a rate of change or tensors. He doesn't have any way of measuring it, but he's bringing this up. This duality is interesting. That's actually the point. So you quote it. All right, so he's going with, okay, continuity is essentially a discussion that appears in the second part when he's talking about uncertain other successions in motion. He points out that every velocity is capable of being increased in intensity and decreased in intensity. Then he's using the word continua in a sentence like, its continuous increase in intensity is called acceleration. Which, if you're thinking very carefully, is very calculus-like. All these definitions represent particular cases of configurations. That is interesting. He doesn't have rate of change. He doesn't have any way of measuring it.
This is a very important point because Aristotle denied the existence of a property of a property. And insofar as speed is a property, there is no space for the notion of acceleration because acceleration will be a property of the property. And Aristotle does not admit this. Here we have the idea that it can be uniformity of the uniformity. So you can have a property of property in some sense. So this is outside of the Aristotelian Aristotelian idea that you can have. Of course, you have not acceleration in our term, in the sense that acceleration is not a magnitude, even not a magnitude by Galileo acceleration. The first time that acceleration appears to be a magnitude with Newton essentially. So acceleration is the phenomenon of the change of speed.
Yep. So again, every time when I'm going back to the original text and I'm reading, I'm discovering something more because that was sort of, hidden gems in the text. No proofs. 2.9. Oresme proposes the comparison of two deformities. The measure and tension to infinity of certain deformities appears later in the third book. Now, you know what? Comparing shape. This is something that's, it's actually done. And it's done in many ways. Comparison geometry. Comparison geometry, it's a modern area of research. He's comparing deformity. This is a very modern thought.
What is the intention to infinity?
I do not understand it fully, but I believe it's something like the trend, how a certain configuration would go, like asymptotic behavior, I would say. But I'm afraid I may misunderstand him. I keep thinking there are certain things I'm not 100% clear, and there are some sentences that are obscure.
Yes, it's possibly the rate in which you become infinite or zero.
But that's again one point that I had to make about being one level higher than whatever he inherited from Aristotle and the old world. That's something that I was interested to pick this up. Then the discussion finite versus infinite appears several times in the third part, and definitely there is added value. I mean, there are sufficient pieces of evidence to think that he may have figured this out by himself because we don't have for all of those. I don't think there is any other source. before 1351. That's something I don't think we have. Good. Good. So we have. Why do I say that this is actually a representation of space? Because these configurations admit space as a particular case. That's a very important point. He's using place, space, as examples of configurations repeatedly and in connection with motion, if he needs to go with that. So we're really here discussing the formation of space. This argument is actually there. We can pick up fragments. Okay, so I was hoping I would have a website to say, but they're gonna release it on November 15. That's the way it is. Now, what's the summary of this first part? By the way, how much time do I have? Because I have material for about 5 hours.
5 hours is too much.
Then you're right at home.
No, nobody can.
If you can
The
stay
doors
here,
are locked.
you can stay here 10 hours, but then we go home.
Yes, no, how much time do we have? Really?
You can go. Generally, we have to stop it before 6. but
Well,
we
I
want
have
to
no idea what
a
time it is.
discussion, So it depends on how much discussion you want to have.
I have content, and the content is interesting. So it's you stop me.
Go.
You stop me.
Go.
Okay, before somebody throws an apple. So the first part concludes with the following summary. First, he gave a correct definition for curvature of planar curves, in the sense that when he's discussing the analogy with circles, that is correct, and we're gonna call a witness on stand. That's gonna be Isaac Newton in a couple of seconds, because the conversation about circles is right there in Newton's work. Then he's applying curvature to understand the behavior of real life phenomena. That is done, including applications to financial mathematics. This is done in the last 2 decades. That's legit. Then we have there a statement in which anticipates the fundamental theorem of curves in the plane. I didn't list here all the other achievements, including the conversation about the turning angle and so on. Only for this is amazing. But then in his doctrine of configurations, that there's this discussion, the graph-like is discussed together with this deformation. That's important. That's important. It's a package. So we have to look at the later doctrines to see how later authors have done it. And we're going to have to go on text for the other pieces of work. All right, so these are the points that I wanted to make here. So when this happened, that was when Chaucer was a kid.
One question, there is nothing similar to the idea of osculation?
No, approximating by circles. I was looking with a magnifying glass.
In Apollonius, there is this idea.
Approximation. Apollonius of Perga.
That's some idea similar to osculation.
What?
I don't remember. No, I don't remember. But there is.
No, that's so approximating a curve by a circle. In Apollonius of Perga, I don't know. But no,
I
okay.
don't remember.
You know what? In conics, there are so many amazing ideas. I wouldn't be surprised. Well, we got to follow up on this.
I
would love to find out. Thank you. All right, so I'm just trying to underscore here the historical context. I'm saying that Boccaccio was writing the Decameron. Petrarch was at work, and he coined the term Dark Ages. And a testimonial for that period is in Froissart's Chronicles. So this is the historical period we're talking about, and here's somebody who's concerned about a doctrine of configurations. That's quite different. So what happened with his heritage? Why didn't the next generation actually pursue? So I'm not entirely sure how the research produced at Collège de Navarre was actually transmitted to students. There is always a problem. You're looking at the institutions and you think about, did they have any sort of formal seminars and so on? I don't think so. Pretty much the heritage is lost. What we know about his citations, definitely Copernicus with the Moneta, that's a fact, but that's not about curvature. That's not about configurations. It's a different deal. So one generation after him, his influence is fading. Now, if you're looking at the revolution of ideas after 1600s, with the concept of curvature appearing, in that interesting research by Huygens with the isochrones, Huygens is not, he doesn't need Orseme. Huygens is doing a lot by himself. And Newton he discovered and developed these concepts fully by himself. So by 1600s, his work was forgotten. Okay, and by the time when Julian Coolidge was writing, only few specialists knew of these texts, and trying to understand this doctrinal configuration is more or less marginal and anecdotic. Although you might remember Dirk Struijk's source book in History of Mathematics, where he's actually, Oresme is cited for pretty much proving that the harmonic series diverges. And that argument that we have in our calculus books about the halves, it's actually due to Oresme. But that's from the proportionibus. It's not from the configurationibus. That's a different work, which was written 3 years before. Okay, so to put the matters in order. All right, so we wrote the piece. It's in this paper, which is in Notices AMS. It happened like yesterday, was like what, 8 years ago, and I should thank you all, because if you remember, Isabel gave the first talk ever about this paper right here at Chapman, long time before it appeared in Notices. And more recently, I asked the help of an applied mathematician, Ana Verdugo, to help me figure out what's going on with certain paragraphs that I was like, you know, do we have mathematical modeling, contemporary mathematical modeling about subjective perceptions? And a couple of examples are valid and could be found in the last 2 decades. So pretty much some of the arguments that Oresme is using are actually quite interesting. Exactly the following 4 ideas: pleasure, imagination as configuration, right? Fear. How afraid are you today on a scale between 0 and 10? And joy. All right. So 1737 is the year when Newton's work, the treatise on methods of fluxions and infinite series, actually appeared. But the work was written in 1671, very likely. So this is when we have the following great gift. It's a systemic treatment of curvature. Like the modern discussion about this figure is actually from there. Right? It's pure Newton. So let's see here what's going on. So Newton has a little polemic slant versus the analytic geometry done at that time. And he's subtle about it. Let's see how he's writing. So what he says is this: instead of doing analytic geometry, how about you're actually thinking about approximating curves by lines and circles, in the sense that you would use really calculus to really understand the geometry of curves. Having observed that most of our modern geometricians, neglecting the synthetical method of the ancients, have applied themselves chiefly to the analytical art, and by the help of it have overcome so many and so great difficulties that all the speculations of geometry seems to be exhausted, except the curvature of curves, and some other things of a like nature which are not yet brought to perfection. To this end, I thought it not amiss, for the sake of young students in this science, he's trying to save souls here, to draw up the following treatise, wherein I have endeavored to enlarge the boundaries of analytics, like going further than Descartes, between the lines we feel it, and to make some improvements in the doctrine of curved lines, and he does. Because what's the fundamental idea of calculus, right? Take a smooth curve, right, and approximate it by lines, right? Well, how about approximating a curve with a circle? Because you're going to the second degree, right? And he's describing the oscillating circle. He's discussing about it as being the circle of curvature as a limiting case of circles that are best approximate the behavior of the curve at the point. That's in Newton. Okay. Between 1671 and 1351 is what? Quite a lot. So the curvature at the point of a curve is the inverse of the radius of the circle of curvature, and Oresme got that right. Okay. Now let's go back and let's try to think about curvature for a surface, because this is the interesting battlefield. Here's why. Suppose we're trying to extend for surfaces the concept of approximating with the sphere, right? So let me show here on the screen with the mouse. Suppose the point is here. On which side shall we put the sphere approximating best the surface? On this side or underneath? Okay, that question is what confused Euler. Okay, so where, if you have a sphere of curvature, how would you deal with that? Well, there's this important work, Recherche sur la courbure des surfaces, that was written in 1763 and appeared 4 years later. It's from the Berlin period, okay? And we have it here, and I'm going to highlight exactly what he wrote. He wrote that we cannot define the curvature for surfaces. He wrote it black and white right there. To know the curvature of the curved lines, the determination of the osculating radius gives us the right measure, presenting us for each point of the curve a circle for which the curvature is exactly the same. But when we are asking about the curvature of a surface, the question, la question est fort équivoque. How do we translate that? It's quite ambiguous, right? Et point de tout susceptible dans réponse absolue. So you don't have curvature for surfaces. And his problem was about hyperbolic surfaces. Take, for example, the catenoid, which he was aware of. What we deal with nowadays, take a tangent point to a point that lies on the catenoid. If the tangent plane crosses the surface, then the point is hyperbolic. All right. For Euler, there was like, I don't know on which side of the catenoid should I put the sphere. That was the issue. So for the hyperbolic points, no idea. For elliptical points, throw the sphere on the other side and you can approximate it. So ambiguous. Well, there have been a few moments when Euler is, surprising us. And besides the fact that he proved everything that's in the Calc 2 book, right? He also has this. The matter is settled in 1827, and I tend to agree with Michael Spivak that this is the most amazing text in the history of geometry. If you read it and if you really understand what he had to overcome, and by the way, it's interesting how Gauss deals with the matter because he was aware of Euler's paper, and Euler's paper is the work that Monge gave to Jean-Baptiste Meunier to reflect on. What was that in 1792? So everybody knew about Euler's paper. Okay, Gauss doesn't cite Euler. Gauss, he's not doing polemic. He's not saying, "Oh, what? Let me correct something that Euler did." No, he's just not mentioning it, not citing it. No, it's just constructing. Gauss being Gauss. What's going on? Take a point on a surface, take the normal to that point, and take all the planes passing through that normal, and the intersections of the planes with the surface are normal sections. Now, the normal sections are planar curves, and you can calculate the curvature for each of them, Newton style. And then, as you rotate those planes, you're going to have an infimum and a supremum for the curvatures. Call them kappa 1 and kappa 2. And Gauss's understanding of the infinitesimal behavior at the point led him, I think it was, I forgot exactly the chapter, in Disquisitiones, the Gaussian curvature is kappa 1 times kappa 2. Now, the other invariant that characterizes shape is the mean curvature. The mean curvature is introduced by Sophie Germain 4 years after Disquisitiones in 1831. It was actually the year when she passed away. Basically, her argument is related to understanding the tension in a membrane. The fact that mean curvature is proportional to tension. That's 4 years before Plateau, right? And whichever is the diversity of surfaces, the curvature, the linear curvature produced at the intersection of the normal plane, which is taking successively all the positions, all the possible positions around the point will give you always a symmetric arrangement. She's making the invariant argument in the construction of H. This arrangement yields what we shall call loi de distribution de la courbure around each of the points of the surface. So she's interested in how you're actually certain quantities are actually changing when you're changing the orthonormal frame around it. She's looking at this. That's a very important point, variational point. And more about this, she's arguing that actually, let's take a look at the cylinder. That's a very strong argument, because if you're looking at it, it's definitely curves. But when you're looking at the principal curvatures, which are 1 over r and 0, do the product and you get Gaussian curvature 0. Well, for Gauss, if you remember in the argument that precedes egregium theorem, he's thinking about developing a surface 1 over another, because the origin of Gauss's quest was to draw a map. He was interested in how a piece of the sphere, which is the Earth, can be actually laid down on a table. So developing the surface over another. This is comparison geometry Gauss style, right? So cylinder, he wouldn't have mind if the planet was a cylinder. But in terms of tension, you don't have tension. If you're taking something made of a solid material and if you bend it, you're going to have tension in it. So in terms of the geometry of the membrane, definitely you detect it. And to detect it, you need the mean curvature. That's Sophie Germain's argument. And she's she's discussing Gauss's work. In the, now, honestly, the geometry of surfaces, it's quite interesting when you're looking at the constant kappa, constant h, and their properties, and that's a whole continent right there. I would, out of those 10 hours that you awarded me, I would spend half of them just to discuss about those invariants and how cool they are. By the way, this is the piece of software that if you are a Mac user, you can download for free from Richard Palais' website at UCI. So if you want to have fun, 3D Explorer Math J, that's a marvel. You can play with that. You can color your surfaces as you wish. That's how I ended up with that.
How should we understand the surface? What is the
but
yeah.
it varies,
Yeah, what I mean is the I see the picture, but I cannot imagine the depth.
Do you like donuts?
So it's
The exterior part of a donut. Just throw the donut.
You have one donut here, another donut.
No. It's the outside. It's the outer shell of a donut. A chocolate donut. Homework. Have a donut. It's like, I'm sorry.
It's only it misses the upper body.
Yeah.
Ah, it's like a tire.
Yeah, exactly. It's like,
Okay.
all right. About Sophie Germain's intellectual heritage, you know what? We're missing a critical edition in English with her works. Number theory, the memoir from 1831, the memoir from the Academy from 1817, plus the essays. That'd be nice. Okay. More on Sophie Germain's work is the paper that I wrote with our colleagues Mihaela and Adam Glesser from Cal State Fullerton, where we looked at the Sophie Germain's academic foundation and her very interesting evolution in time, everything documented in the essays, and we felt like the essays deserve more consideration, more attention, and we looked at with great pleasure into her writing. When did we write this? When was that? Because during the coffee, because it was like, okay, I forgot when we wrote it. This is how bad it was. So yeah. So
Anyway.
I mean, just imagine to have somebody doing a work like me being prevented to talk about Orseme today. That'd be like, it's like, oof, couldn't stand the idea.
Also, they didn't-
1817, if you're talking about that. So we cannot blame the emperor, as usual. Okay, now the issue that I wanted to bring in here, it's about minimality, because if we are discussing the formation of space, there is this other thing, what is the best way to discuss about representing space? And I wanted to take a look at this from every possible angle. And talking about minimal surfaces, it's something that we should look into it. I will rather bring in this argument later on in the most elementary way I could. I don't want to say anything advanced today. There was a lot of tension about, basically Gauss delayed publishing Disquisitiones, and the way he wrote Disquisitiones was very careful at that time. And the problem had to do with how hyperbolic geometry at the beginning of the 19th century, I'm pretty sure everybody here in the room knows more about that than myself. But there was a lot of reluctance into the way we view those geometries where the sum of the angles in a triangle are not necessarily 180. What do we do with that? Okay, and remember, this is actually consistent with that point where Euler was confused about hyperbolic surfaces. There was a lot of clarification brought in once you understand what happens and what are the properties when kappa is strictly less than 0. That's something else. So Immanuel Kant, mathematics and physics are two sciences in which reason yields theoretical knowledge. Mathematical and physics have to determine their objects a priori, and that means that knowledge is absolutely independent of all experience. Space, in particular, is a necessary representation underlying all intuitions of what lies outside us. We cannot imagine the absence of space, only space empty of objects. It is pure intuition because we can only imagine one space. In consequence, geometric propositions can only be derived from intuition and not from concepts alone, and that the derivation is a priori. If I summarized it incorrectly, I apologize big time, because again, I'm not an expert. I'm far from being an expert. My only question is, and I can't answer this, why did Gauss publish so late when he definitely had it earlier? This was definitely the dominant viewpoint in many European universities at that time. But nevertheless, when Gauss is reading the János Bolyai appendix in 1831, he's writing back. To praise it, it would amount to praising myself, for the entire content of the work coincides almost exactly with my own meditations, which have occupied my mind for the past 30 or 35 years. And you know what? I believe him. I believe the chronology is accurate. And that means that the matters could have been clarified since about maybe before 1800s. What was the issue? The issue is about sum of the angles in a triangle and how do you represent that? It's about very consistent with that lack of understanding of behavior of hyperbolic surfaces. And if you're looking, there is this tension in, it's what are you doing with curvature in general? What are you doing with understanding the local properties and the geodesic properties of hyperbolic geometries? Really, that's what it is at stake here. So why am I looking into Gauss with so much care? Because Gauss assigned Riemann the homework. So in order to understand Riemann, you actually have to understand Gauss's motivations in getting here. So nevertheless, the problem of various different geometries was a central problem for math and philosophy in the first half of the 19th century. That's well known. Gauss is asking the candidate to write a work on foundations of geometry. And this is the context in which the concept of Mannigfaltigkeit appeared. The idea of manifold appeared as a challenge, and it was, 8 or 9 months before Gauss's passing, and Riemann was young, was what it was believed to be the beginning of his career. But nevertheless, we're going to get here the mathematical representation of the idea of space. Now, what is space? How do we deal with that? Here we have to stop for a second and reflect about the following. What is the legit representation of the idea of space? Because for more than 150 years, this was manifold, and this was introduced by Riemann. But nevertheless, today, we have a variety of other representations, like solutions or certain PDEs. That's representation of space, that's legit. We're talking about solitons as representations of space. That's legit. After Grisha Perelman's proof, the idea of representation of space changed. We are here in the aftermath of a change of paradigm, and that's why we're very much, we understand very well what changing of paradigm means. But the idea of manifold, that appeared, and it's actually something that changed the whole tide in the way we did geometry. And if we're looking very carefully, so the argument I was making at the beginning is like, you have this package, you're discussing about a representation of space, and in the same time of its deformation. This is what Riemann does. He's not only talking about manifoldness in Clifford's translation, but curvature appears as well. And that's important. Okay, what is space? Philosophically, the theme is like really old. How old is that?
Nice question. What is space?
How about let me call a witness, Bertrand Russell, who's discussing Plato's Timaeus, and he's pointing out to a fragment where we read this. There is one kind of being which is always the same, uncreated and indestructible, never receiving anything into itself from without, not itself going out to any other, but invisible and imperceptible by any sense, and of which the contemplation is granted to intelligence only, and there is another nature of the same name with it, and likely perceived by sense, created, always in motion, becoming in place and again vanishing out of place, which is apprehended by opinion and sense, and is a third nature, which is space. What's going on here? And is eternal, and admits not of destruction, and provides a home for all created things, and is apprehended without the help of sense by a kind of spurious reason, and is hardly real, which we, look at this precision, beholding as in a dream, I was joking, say of all existence that it must of necessity be in some place and occupy a space, but that what is neither in heaven nor in earth has no existence. All right, you know what? Bertrand Russell says this is a very difficult passage.
What is the Greek?
I don't speak Greek. I can barely handle English. If it's, of course, Bertrand Russell, philosophy of Western.
No, the passage of the Plato.
It's Bertrand Russell. It's cited by Bertrand Russell. It has all the coordinates in all the references. Let me take a peek and get back to you with the exact quotation because I wasn't wise enough to put it right here. Okay, what is space? How about a manifold instead of that? Here's an offer you can refuse. Because, go ahead and read Bertrand Russell. This is absolutely, it's beautiful. But what he's pointing out, in general, it is fanciful to find analogies with later philosophers. But I cannot help thinking that Kant must have liked this view of space as one having an affinity with his own. Maybe he's quite subtle here. Anyways, let's go back and let's try to understand what a manifold is in Riemann's construction. And it's done just perfectly, 1854, in translation, in Clifford's translation. And he's starting first with a relationship with an argument that this is a problem of interest to philosophers as well. He's arguing right at the beginning. It is known that geometry assumes, as things given, both the notion of space and the first principle of constructions in space. She gives definitions of them, which are merely nominal, while the true determinations appear in the form of axioms. the relation of these assumptions remain consequently in darkness. We neither perceive and how far the connections is necessary, nor a priori whether it is possible. He's careful here. He's trying not to irritate his target audience, which was the administration at his university at that time. We know the context, it was complicated. From Euclid to Legendre, to name the most famous of modern reforming geometers, this darkness, that's about the relationship between the axioms and the principles, was cleared up neither by mathematicians nor by such philosophers as concerned themselves with it. So the problem of representing mathematically space was serious as of 1854. The reason of this is doubtless that the general notion of multiply extended magnitudes in which space magnitudes are included remained entirely unworked. Correct. Now, he's going to actually need to import Pythagorean theorem in n-dimensional magnitudes. He's preparing that. I have, in the first place, therefore, set myself the task of constructing the notion of a multiply extended magnitude out of general notions of magnitude. That's what we call today the Riemannian metric. That's what is going on here. It will follow from this that a multiply extended magnitude is capable of different measure relations. And consequently, that space is only a particular case of a triply extended magnitude. Good. Again, a doctrine with a particular case. In proceeding to attempt the solutions of the first of these problems, the development of the notion of a multiply extended magnitude, I think I made the more indulgent criticism in that I've not practiced in such undertakings of a philosophical nature, where the difficulty lies more in the notions themselves than in the construction. His approach is constructive. He's not trying to irritate the Immanuel Kant fan club, and it's just a constructive approach. But he's arguing that he needs more than 3 dimensions. He needs to spend time to argue about it. And that, besides some very short hints on the matter given by the private consular Gauss in his second memoir on big quadratic residues, where, of course, we're talking about n-dimensional quadratic forms. And then in his Jubilee book, we're talking about disquisitiones here. And some philosophical researches by Herbart, I could make use of no previous labels. These are the sources, that's right, that's it. So the construction, what's he meaning by magnitude notions are possible where there is an antecedent general notion? So takes a domain and maps the domain on the abstract manifoldingheit. So pretty much is what we call today a patch or a chart in the atlas. That's what's going on here. According as there exists among these specialization a continuous path from one or another, they form a continuous or discrete manifoldness. He's going to kick out the discrete case. He's going to deal with the continuous ones. His reasons for continuity are entirely different than the ones that Oresme had. Entirely different. But so here we could discuss what kind of metrics are there. We could discuss whether the class is just continuity or he needs more. That's a longer conversation. The individual specialization are called in the first case points, in the second case elements of the manifoldness. Then the atlas. And he's calling the charts in the atlas, they're called quantas for him. The comparison with regard to quantity is accomplished in the case of discrete magnitudes by counting and then by measuring. These measuring are actually mappings between images on the charts. Measure consists in the superposition of the magnitudes to be compared. It therefore requires a means of using one magnitude as the standard for another. He's not really meaning measuring. He's more like this idea could be due to the developing one surface over another from Gauss. We can see here an idea imported from disquisitiones. But then, touchdown right here. To give an intelligible meaning to the curvature of an n-fold, extend at a given point in a given surface direction to it. You know what? Hope you don't mind. I'm gonna definitely draw this. This should be translated in a drawing because we're gonna have a problem here. And it's better to handle it step by step. Okay. So. Okay, this has dimension n. So we are at a given point of a given surface direction through it. What's that? A given surface direction. He's going to actually import the concept of Gaussian curvature into the n-fold. But for that, he's going to need a bundle of geodesics, like this. We must start from the fact that the geodesic proceeding from a point is entirely determined when its initial direction is given. So here's the geodesic, and the initial direction is a vector. Let's call it V. Okay? So he's going to take another direction. Let's say this is U, all right? And these two are forming a plane. Then he's taking the bundle of all the vectors in that plane and all the corresponding curves. They are generating the surface, and the surface lies inside the n-fold. Okay, that's the construction. According to this, we obtain a determinate surface if we prolong all the geodesics proceeding from the given point and lying initially in the given surface direction. This is the surface. And that's the description. This surface has, at the given point, a definite curvature, which is also the curvature of the n-fold continuum at the given point in the given surface direction. So pretty much is working pointwise. And at this point, the curvature for the bigger thing is the curvature of the surface hereby generated. All correct. Okay. But look at this precision compared to what we had before. But nevertheless, he's discussing about representing space. He's distinguishing this problem from the philosophical issue. And then he's bringing in the package deformation. We call that today sectional curvature. This is where the sectional curvature comes from, 1854. Now, you know what? I made my point. Otherwise, I would have more extensions going to John Nash and the embedding theorem. But I think once the point in the title is being made, this is the best place to both Riemann and Orseme at the same time and say, you know what? This is the story I had to tell you. Okay. Yeah, thank you.
Question, remark, objection, protestation,
Complaints, suggestions for improvement.
suggestion for improvement,
The type of thing.
complain, what you do? Kind, or what you do?
Did Riemann know Aura? Read Aura?
I don't know. Let me take the fifth. I don't know.
But why is that such a difference?
I should have Riemann's file. No, I really I don't know.
That's not like the old.
You said that by
Hold on.
the 1600, Aura was already forgotten, but how influential was he in his lifetime or immediately after his lifetime?
Okay, when you mean influential, you mean in the political circles
Or
or
I mean, scientifically?
or scientifically? So see, I don't really know. Here's why, because you could, what I can do, I can read him, and you could see him repeating over and over again certain claims, like he's not believed, like nobody's listening to him and so on. And somehow living where? College de Navarre, and then in a cathedral, and then from time to time, you're going over to the court. I don't think he ever felt that he had influence.
Just, I wonder if there were other scientists who read what he wrote.
In the same period, a similar idea was developed at the Merton College by the Super Merton. And so there is a circulation of this idea that is trying to well tested by the work of Graduate.
Wait. When you're saying this idea was invented at
No,
Merton
I'm not speaking of the idea of curvature, I'm speaking of the idea of the
of configuration.
extensive quality.
Yeah, okay, agree on that.
The idea of quality, frankly, of the idea of curvature, the first time on my life that I, it's not what I'm speaking about. But I don't remember whether in the text, but there are very good works by Edith Siller on the Mertenian and Merton, for example. So this idea right up to Galileo, the theorem of Merton Coolidge, that is also included by Orseme, is also one of the fundamental theories. And the other is by Galileo, the theorem of that essentially the derivative of the X2, that the time, the space covered by the uniform accelerated motion in a certain time is equal to the space covered by the uniform motion with the speed in the middle part of the time. Okay, so this is still one of the fundamental theorems in Galileo, and is proved by Merton and by Merton College and Orseme, and apparently there is a circulation, so Galileo has. So certainly the great influence of this factor. For the question of intensity quality, for the question of Curvature, frankly, never.
Right.
I know the first time that I heard speak about it.
Okay, let me tell you how I got into it. So I owe this idea to my advisor. Bang Chen wrote a survey on Riemannian submanifolds back in 2000. And I was at Michigan State at that time. And in one of the first paragraphs, it was that the idea of curvature appears first at Nicole Oresme. She was indicating the chronology. And I was shocked, because I thought I knew a little bit of Middle Ages, and there was nothing that was gluing in any way with this. And I said, you know what, someday I'm going to go back to this and I'm going to start reading the source to see what's going on. And by the time when I started to read, and that was like 2014, I was reading like a geometer, really, and I didn't know anything of the philosophical subtleties of this. In the without the help of Marshall Claggett and Edward Grant, I would never understand a thing. But the geometry was not continued. That's a fact, because if you're looking at the theme of curvature, it's Huygens with the isochrones implicitly, but the real deal was with Newton. That's what's going on. So Orseme is a singular case in many things, and that part of his work, the doctrine of configuration, maybe he was very impactful in terms of the books against astrologers, the work on the Moneta and so on. But the doctrine of configurations didn't really make school in his century. Am I wrong to say that? I mean, if anybody can find some impact of that work, I'd be very grateful to find out. Because I've been trying to, because I found it like a very useful piece of work, and it was not continued. What a pity. This story has a lot of delays in it, like the little mishappening with Euler, and then the delay that Gauss had. It's a lot of delays in here, and a lot of other things could have gone better in terms of advancements of how to calculate things, location, position, if the matter had been going on differently. Please.
I have a sort of like general question. The standard narrative that one hears about mathematics is that within Europe, we had these dark ages, the Middle Ages, but there basically were no progress within mathematics. And I was wondering, so this, when you increase the resolution and you look a bit more at what was actually going on, for instance, we find that you pointed out today, this right over that actually had all of these mathematical notions. And I was wondering, what's your general take on this narrative of them not being within Europe, very much like mathematical progress, but in the Middle Ages?
Thank you for this question, but this example, I'm going with Dirk Struik here. We have, so Nicole Oresme is, according to Struik, an outlier. So he's not pertaining to any rule. He's not following, he's not coming from a school of mathematicians that were trained informally in a university and had students, and nothing like that. He's an isolated case and we should not produce an illegal case of induction by assuming that Europe at the time was as smart as him. Not the case. So he's inventing a whole theory for his work. And I mean, how many people can actually do that? This is something really in a league of his own. That being said, if you're looking at the history of, I mean, another exercise I made, I looked at going back to early Middle Ages, to Isidore's etymologies. Isidore's etymologies is full of examples of how mathematics was misunderstood and completely lost, together with the loss of Greek language. When they lost Greek language, there was a complete disaster in terms of how much was kept in the West. So that's why it's kind of, you're wondering what kind of library did they have at College de Navarra. I have no idea. I would love to see a catalog of the books they had. We have here a couple of traces, and definitely he knew Euclid when he was working on his master and so on. That we know, but it's very little. So it was really Dark Ages. Because I don't want to give you the impression, you know what, they were like 100 like him. Oh, I wish. I wish.
Ahmed.
So we have at least two deep between Oran and Riemann. This differential geometry question, and also the zeta function, because they consider the harmonic series divide by what very much zeta function. So,
Right.
and what is interesting is that he proves that the harmonic series in development is absolutely fabulous.
Absolutely.
This is something that we can teach to our students today without any problem. Now he found some trick by grouping terms, and from here he okay. So this kind of argument was not popular at that time. So there is something history to make grouping of the terms of the series, and also I think he is the first one to prove that to give the geometry series.
So it's so
is there any philosophical reason behind this kind of consideration?
I think you're totally right. I think we're looking here at a very original thinker with fantastic mathematical intuition. And I wish he had more background to see exactly what fully he could have developed. But at least these two things, and let's not ignore the moneta, because that's really applied mathematics per se. And so he's really the work of mathematical genius in a century where mathematics was not the strong point of the society. And it's quite interesting if you're looking at the way he's using mathematics. Because suppose he was writing for the king to convince him about a certain assertion. You know what he does? This is something that you shouldn't try to do today because you're losing the debate. He's using mathematics. He's using the mathematical argument, and he's using the doctrine of configuration as an argument to convince people about when they're wrong. Okay, try to do that today. To come up in a public debate with a mathematical argument, you're losing. But at the time, he's very positive and hopeful. Besides the fact that he has massive insight, so definitely, I mean, the story with the harmonic series, that's absolutely amazing. I think this is in the same period, right after the Black Death passed away. In the first few years, right after, he's writing a lot, and it's a lot of mathematical substance. What he's doing later on is more of politics, translation, adapting into French vernacular, some of the earlier works, including the work on the sphere. But the genuine research work is done when he's around 30-something, and he's still in Paris at College de Navarra. So let's call it a moment of genius. Am I exaggerating?
You mentioned Gauss and how he delayed his publication of the publication of his work in geometry. And did you show a letter to Farkas, and he says that, well, I have been thinking about that for the last 35 years. But then in the next paragraph, he says, I never intend to publish anything of this. I just intended to write it and just that someone else finds it when I'm dead. So he cannot be talking about this.
Let's think about what is this at stake. So if you have a hyperbolic surface, the curvature is negative, right? And on such a geometry, the geodesics are forming triangles whose sum is less than 180. This is the issue at stake. That part is not in this Disquisitiones, but the object is that it's let's say it's a hyperbolic surface. We're discussing about hyperbolic surfaces, and I'm pretty sure he got that. He understood very well what happens with geodesics. What happens? He knew that once you have the definition of curvature clearly, you understand the infinitesimal behavior of that. So he knew that. The question was how much is leaking out, because he was kind of interested in his reputation, his credibility, his prestige at that time, and he was like, okay, everything that's controversial, let's don't include it.
So you think that he delayed the publication of the Disquisitiones?
Yeah, that is definitely. Maybe a few years, maybe he wrote it later, but I wouldn't know. I mean, we're discussing about the chronology when Disquisitiones, I mean, is the claim from 1831 that he knew about the geometry of hyperbolic surfaces even from 30 years before. Should we believe him or not? And I tend to believe him. But then what are we doing? So let's take a look at the tantamen. Just one second. Let's take a look at the tantamen and see what's going on there. So pretty much you're dealing with the first 4 postulates in Euclid, and you develop a geometry, and you see how much you can prove, and it's a pretty consistent geometry, and you're going on for what, 70 pages where you prove stuff that happens in Euclid just based on the first 4 postulates. That's perfectly legit, and I'm pretty sure that if you start with a differential geometric approach for the geometry of surfaces, you get the same results. So he's believable. He's believable. Yes, please.
Yeah, I think we even have a letter from Gauss to someone where he says, I think I don't remember when he was young, and where he says something about having discovered like a wonderland of new geometries or something, and where he says he also can be like triangles, can make them bigger or smaller. You have different like the sum of the angles. I think we actually have a letter where he says so. He doesn't do the mathematics in the letter, but he describes all of the non-Euclidean geometry. So I think he should be believed, but I think we actually do have this letter. I can see if I can.
Yeah, I believe him, but I was wondering whether in this comment he's referring to this.
Yes.
He's definitely not in a position of power. I mean, what he is, he's a counselor to political crown at the time. So he cannot change the trend in Europe. If he's publishing it, he's calculating who's going to understand it.
The training would challenge Kant.
Hmm?
Is that the problem?
Here's what I think the problem is, and I might be wrong. How do we represent hyperbolic geometry? How do we understand? I mean, do we agree with the fact that we can replace straight line, by a geodesic in hyperbolic space? Think like this. Think of the inner part of a donut. Do you agree that the geodesics on they're like those helices that are around the torus, and you're looking at that? Do you agree that if you're forming there a triangle, this could be viewed as a triangle? Is this legit to call it triangle? Okay, what is your intuition saying about this representation of the idea of a triangle? Because if you are rejecting this as being a legit triangle, then we have a problem. And I don't believe he believed that he could be sold the idea. So again, if I misunderstand it, then the argument with the publication being delayed doesn't hold. But that was what at the stake. Because to understand the triangle and sphere, the elliptical case, I don't think that was a problem. The problem was with the hyperbolic surfaces. And that's inherited from 1763. I mean, there was much confusion about that. But this is what I try to deliver today, and I thank you very much for this opportunity. I never had a chance to discuss anywhere else on this planet the problem of curvature. I mean, where is this coming from, and what's going on, and how much headache this actually, because if this was 100% clear, we've gotten the kappa 1 times kappa 2 from the first attempt, and everybody would have been so happy. And the geolocation, so that we can be tracked with these beautiful devices, would have been possible earlier with 200 years or so on. But no, this was the outcome of a serious battle of ideas.
Thank you very much.
My pleasure. Thank you.
We have a very brilliant mathematician colleague